Hello again, everybody. This is another lecture in the series of sonography instrumentation, part of the physics ultrasonography. And in here, we will talk about the receiver here. Okay. Uh, in this instrumentation, we need to know something about what is the pathway of ultrasound instrumentation. So we start by the pulsar. The pulsar is sending the electric voltages, and they are determined. In the pulsar, we have the PRP, PRF control, we have the output power control, and we have the frequency selection is coming out from the pulsar. And then the electric voltage is given to the beamformer. The beamformer will do the steering of the beam, will do the focusing of the beam, and the apodization. And after that, this electric voltage is given to the transducer. The transducer is converting this electric voltage to sound waves. Sound waves are given to the patient. Patient will get reflections back. These reflections will hit the transducer again. They are converted to signals. Signals are traveling through the electric signals. I mean, they are traveling through the cord back to the beamformer, and the beamformer, these electric voltages are exposed to the dynamic focusing and the dynamic aperture. After that, these voltages after coming here from the beamformer will be delivered to the receiver, and this is our topic today. After the receiver, this after being converted now to the video modes that we are going to know in a moment, these video modes are given to the scan converter, and the scan converter will convert this to an images, and images or frames are sent to the display. So this in short the whole journey. And the receiver here, it has 5 functions, and we'll come to this in a moment now. So here are the 5 functions of the receivers. We have amplification, compensation, compression, demodulation, and rejection. All these are in here in the receiver. So we start by the amplification, and amplification is generalized amplification of all the received voltages. Is it adjustable? Yes, we can adjust it by the control units. What are the control keys? We have, it's called the gain, or the total gain, or the overall gain. This gives me an idea that is magnifying everything. Okay, so it affects the brightness of the image, making it brighter all over. Okay, so it's the entire image is amplified. The entire image becomes brighter from all the echoes. Okay, all the depths, for example, shallow or deep, they will be magnified, brighter. All the levels, meaning that the low level or mid level or high level echoes, they will be magnified. So the low level might be becoming mid level echoes. The mid level echoes will be magnified to or high level echoes, or high level echoes will be magnified because super bright echoes. So it means that all the levels are magnified. All the origins, what does it mean all the origins? The signals are coming from the patient, or the noise that are coming from the surrounding. Also, all of these are magnified. So the magnification here is not selective, it's generalized. Again, it has a control called the gain, or the total gain, or the overall gain. What are the units of magnification? Okay, they are known as decibels. Okay. Please go back to the video of signal to noise ratio to know something about the signal to noise ratio here. So we have here some examples of how amplification is going on. Okay, we have example here of the decibels, because as we mentioned earlier, amplification is by the units of decibels. So let's understand something here. Okay, assume that the received echoes, or the received signals that are coming from the beamformer to the amplification to the receiver is in the 50 milliwatt per centimeter squared intensity. And you put 20 decibel amplification by the amplifier, by the gain. Okay, what will be the value of the 50 milliwatt per centimeter squared? They will be 5,000. To know how this happened, okay, we need to understand that decibels, they go by plus or minus, added or subtracted, the changes of decibels. So 20 decibels, they can be understood as 10 plus 10, 10 plus decibel, 10 plus decibel. Okay, they are equivalent to how many value in the numerical value or the numerical magnification. Okay, each 10 is equivalent to times 10 evaluation or magnification. So plus 10 decibel is equivalent to times 10. Plus 10 decibel equivalent to times 10. So times 10 times 10, it equals to times 100. So the 50 will be multiplied by 100. I will get 5,000. This is how we do this math, or we do this calculation. You might have a example in the exam about the amplification. You can do that. If attenuation, you can do that too. So this table or this format, it will help you to go from here down to this area, from the higher intensity to the lower intensity, and this happens with attenuation. Or with magnification, amplification, this goes from the lower intensity to the higher intensity again with the amplification. So this format or this table shape, it helps you to understand how amplification happens and how attenuation happens too. All right. So let's go for another example. Another example. Again, this is the same chart. Okay, you can use here the lower intensity, the ratio, and here is the higher intensity. Okay, in magnification, you go from the lower to the highest. So I put here the lower value. For example, they give you the lower value is 90 milliwatt per centimeter square, and you added 9 decibels. So what happened? Okay, how much will be the higher intensity after the magnification? Okay, so you give the 9 decibels. Again, 9 decibels will be broken down into 3 plus 3 plus 3. Again, we mentioned that decibels, they go by plus or minus. So 9 decibels, they will be broken down to plus 3 plus 3 plus 3. This is magnification, okay? So these decibels, that plus 3 plus 3 are equivalent to how many in the true life value. So plus 3 decibels is equivalent to times 2. Plus 3 decibel is equivalent to times 2. Plus 3 decibels are equivalent to times 2. So again, what happened here? Times 2 times 2 times 2 means times 8. Okay, so the 90 times 8 will be 720 milliwatt per centimeter square real intensity. The value, the new value, okay, it will be 720. Again, this format, it can be used if you want to calculate the attenuation. All right, so you put here the higher value here, and will be attenuated to this direction. Okay, so we'll come to this when I discuss the attenuation after some time. Okay, and I will show you how to do this from the lower intensity to the higher intensity in magnification, or higher intensity to lower intensity if we are talking about attenuation. Another example with magnification. Again, we have the lower intensity and the higher intensity, and we have here the ratio. The ratio will be in two forms, either the decibel format or in the real life numerical format. Okay, we have here a very low intensity, like 8 milliwatt per centimeter square. Okay, and we apply 32 decibel of magnification. Okay, what happens here? Okay, what will be the real value later on? We apply 36 decibel. 36 decibel can be broken down to plus 10, plus 10, plus 10, plus 3, plus 3. So these are 30, and these are 6. Okay. What happens here? The plus 10 is equivalent to times 10. Plus 10 equivalent to times 10. Plus 10 equivalent to times 10. Plus 3 equivalent to times 2. Plus 3 equivalent to times 2. This is here again, we knew this, that, or these are the two values of the decibels that we are dealing with in the exams. Okay, there is a lot of values for the decibel, of course, how they are equivalent to how many multiple in the real life, converted to the real life magnification or attenuation. But in the exams, we need to know that plus 10 and negative 10, okay, or the plus 3 and negative 3. These are the only two values that we're dealing with in the exam. So that's why I keep them in here. So 36, these are 30 and this is 6, okay? The real value is here. So these ones, if I multiply them all together, they will be 4,000. So I'm having here 8 and magnify times 4,000. I will get here 32,000 milliwatt per centimeter square. This is very, very bright. So again, as we see here, if I put 36 decibels only, okay, numerically it looks like smaller number, but actually it is converted or equivalent to very high number in the real numerical life, which is 4,000. And this will the final end. Okay, again, put this frame or this chart in your mind when you go to the exam, the SPI exam. Make sure that you put this. This is here the value. This is the starting one, and this is the ending one. Okay, and you put here is it magnification or attenuation. If magnification goes by pluses, attenuation they go by minus. Okay, in the magnification in the numerical value, it will be plus times, and in the attenuation will be divide. So that numerically it goes by multiplication or divisions. So now we come here to the image brightness, and we knew that if I'm making the pulsar output power is increased, I will get image brighter. If I go to the receiver and increase the gain in the receiver, I will get the image brighter. So what is the difference? Both in the pulsar and in the receiver, I can have function here, a function, both are making the image brighter, either output power or gain. How can I make the difference, or how can I understand the difference? Okay. To understand the pulsar, the output power here, if you increase it, what happened? There is a higher voltage delivered to the transducer, higher output power, so the patient is exposed to high output power sound waves. And then the reflections will be more stronger reflections because there is high output power transmission. I will get high received signals, and this will be processed along the whole journey here, and they will appear here as bright echoes. So the pulsar, the output power, is exposing the patient to high output power sound waves. Now we come to the gain. If I manipulate the gain, what happens here? The gain will be in the receiver. If I do anything here, it will not touch the patient. The patient, the same output power, the same received signals, they are all the same. But when they come to the receiver, they are magnified. So am I exposing the patient to some increase of the voltages? No. With the gain, I'm not doing anything or touching the patient. I'm just manipulating the received echoes, will make them brighter, so the image again will come brighter. Okay, so this is to know the difference between the pulsar output power and the receiver gain. What is the difference, the main difference between these two? Okay, changing the image brightness through the output power is exposing the patient to some voltages, to some increased intensities, and the patient here will have what we call a high bioeffect. The opposite will happen when I go to the receiver gain. If I'm increasing the brightness of the image through the total gain, what happened? The patient is the same. I'm not touching the patient. The patient is not exposed to ultrasound waves, extra ultrasound waves. Okay, the patient will have the same bioeffects that that was beforehand. So I'm increasing the output power. I'm exposing the patient to extra bioeffects, increasing the brightness through the receiver gain. I'm not touching the patient. The patient is having the same bioeffects that has been before. Okay. So this goes for what we need to know about the Alara principle. So this is here for the we apply this principle on the Alara. What is the Alara principle? Is as low as reasonably achievable. Okay. What would be the situation? I want to apply the knowledge that I just mentioned before, apply it to keep the patient as safe as possible. So what shall I do? If the image is dark, I want to make it brighter. I don't want to expose the patient to output power, extra output power. So what I need to do here, I'm magnifying the gain from this step to the display. I'm not touching the patient, so I'm increasing the overall gain. I'm increasing the overall gain. Okay, I make it the image brighter through this step. What if the image is bright? This here is too bright. I want to make it darker. Okay, I can lower the gain or lower the output power. No, I lower the output power. Why? Because now the patient, I'll get some benefit to the patient. What is this? If I'm lowering the output power, I'm lowering the bioeffects that the patient is exposed to. And that's why I can get the image here darker, while I'm in the meantime, I'm getting rid of the extra bioeffects to the patient. So I'm saving the patient by the lowering the output power. So if the image is bright, lower the output power to make the patient less in the bioeffects, and in the meantime, I will get the image darker. All right. The second function of the receiver is compensation. Compensation means what? Is compensating for something that has been lost. What is the loss here is the the strength of the sound waves as they go through the patient, they are exposed to attenuation. So when they come to the display here, the deeper part will be darker, the superficial part will be brighter because of there is a process of attenuation here. So compensation here is for what? Compensation for attenuation, right? So this compensation, is it adjustable? Yes. And what are the key controls? The key controls are the time gain compensation, TGCs, or depth gain compensation, and the name is DGC. So both are the same. What is the function of these TGCs or DGCs? Okay, they are number one, compensating for attenuation, I just mentioned it. But also you can adjust the brightness of the image, okay, make it more homogeneous brightness. So if you look at the image and you see that some areas or some levels, for example, the far field or the midfield or the far or the deep field, they are not in the same homogeneous brightness. I can adjust also the homogeneous brightness of the image through the TGCs. All right. So again, the TGC's function has two functions. Number one, compensate for attenuation. Number two, make the image of a homogeneous brightness. Okay. Units are decibels. Again, we mentioned this before. So this is how we adjust the curve. We have here, if you study the TGC curve, there's here this, there are sliding bars. We know this, okay? The upper part is called for or is used for the near field brightness. The mid part, we call it the slope. This is used for the midfield brightness. And then the lower field or the far field brightness is controlled by the last few sliding bars. So these sliding bars are called for the far field, this is for the midfield, and these are for the far field. Okay, this is the midfield is called the slope. This is because the TGCs are adjusted in a slope way. Okay, so this area here also, the last part of the slope is called the knee. You need just to know this, right? So this is here the description of the TGC's controls. If I slide them to the right side, your right hand side, I'm getting plus decibels. If I slide it to the left in this way, I lower the decibel. So increasing the decibel right to the right side, slide it to the left, I'm lowering the decibels, right? So making here brighter darker, brighter, darker. Now somebody will say, okay, if I'm using different frequencies, am I having the same TGC map, the same TGC curve? Okay, actually they are not. Why? Because we know that we're using TGCs to compensate for attenuation. So if I'm having more attenuation, I'm getting more. I need to move the TGCs more to the right, this way. So with the high frequencies, I move the probe to the TGCs more to the right. Why? Because high frequency are easier attenuated. So I'm having more attenuation with the high frequency. That's why I will notice the curve is assigned more to the right side. What if I'm using lower frequencies? If I'm using lower frequencies, I will notice that the curve is more to the left. Why? Because lower frequencies are less attenuation. That's why the curve goes a little bit to the left. Or you'll notice that it's going more to the left. So this is the curve how it looks like if you're using high frequencies. And this is the curve how it looks like if you're using lower frequency. Why that? Because high frequencies are more attenuated. So high frequency, more attenuation. The curve will go more to the right. And the slope here, this is the slope, it starts early in the curve. This is here where the slope is seen. This is the starting of the slope. You see, it's higher. When you come to the lower frequencies, the low frequency, the curve is more to the left, right? Left curve. This is the low frequency. The curve is more to the left, and the slope is late. So you can see here, this is the slope. Okay, late slope. The slope starts late, and the curve is to the left. Okay, if you want to some way to memorize them, the lower frequencies start with L. The curve is to the left, starting with L, and the slope is late and starts with L. So this is somehow it will help you to memorize the TGC curvature if you are dealing with high frequency or lower frequency waves. A famous question. What is this question? Okay, you are using 4 megahertz probe. So this is the frequency of the probe. How many decibel of compensation needed at 10 centimeter depth? Somebody will say, okay, 10 centimeter depth means that I go to the image at a depth of 10 centimeter. How can I know? Okay, this is easy because again, TGC compensation is to compensate for the attenuation. Can I calculate the attenuation at 10 centimeter depth? Yes, we know that there is something called attenuation coefficient. Attenuation coefficient for the soft tissue in the human soft tissue is known, okay, is 0.5 decibel per each centimeter depth per 1 megahertz probe. So you can calculate now how much will be the attenuation at 10 centimeter with 4 megahertz. So I calculate this way. This is 0.5 decibel per centimeter per megahertz. Multiply by 10 centimeter depth, right? Multiply by 4 megahertz probe, okay? That will get 28 decibels. So 20 decibel, this is the attenuation happens at negative 20 decibel. This will be attenuation happen at 10 centimeter depth using 4 megahertz probe, okay? So if I want to compensate, this is here telling you what will be the compensation. Compensation will be what? The same attenuation, but in the opposite way. So the opposite way would be that 20 decibels. So I need to compensate the TGCs at this depth by 20 decibels. You move the sliding bar at 10 centimeter to the right side, adding decibels to the right side, adding decibel to the right side. I'm repeating this many times. So if adding decibel to the right side, how many decibel? 20 decibel. So when I move that sliding bar to the 20 decibels, this is I'm compensating for the negative 20 decibel that happened with attenuation. All right, guys? So this is how to answer this question. If you're using whatever the megahertz and they ask you whatever the depth, how much the compensation for attenuation. You can calculate the attenuation based on this formula. Okay, this is here. This is the formula I'm using. The soft tissue coefficient is 0.5 decibel per centimeter per megahertz. All right. Now we come to the third function of the receiver, which is compression. Compression is compression of the dynamic range. Is it adjustable? Yes. How this control key is called? You might see the word dynamic range or the log compression, or compression, or grayscale mapping. All these are the synonyms for the word compression. We must see this in the ultrasound machine. Again, what is the compression? We mentioned that compression of the dynamic range, narrowing of the dynamic range, DR. The units are in decibels. So what is this dynamic range? Dynamic range is the ratio between the highest to the lowest values for any component, assuming that the highest value is 500 and the lowest value, for example, is 10. So what is the ratio? 500 divided by 10. Okay, I will get the ratio is 50, right? So this is the dynamic range of this value is 50 because I'm having the highest 500 and the lowest 10. Okay, so this is dynamic range. Dynamic range actually is specific for many components inside the machine. Right? For each component has its own dynamic range. Some of them are having 50, some are having 80, whatever, right? So what is the compression? Compression, actually, there are two types or two pathways of compression in the ultrasound machine. There's a compression that is going on all over the system, and this is for the voltages, electric voltages that are running through the components here, and these electric voltages are going less and less as we go to the display. So there is here a series of compressions along this system. This series of compression is for the electric voltages. Why? To fit the dynamic range for each system component. There's another compression, and this is what we are looking for more in this part of the discussion, which is compression of the shades of gray. Shades of gray of what? Of the display. So why we mention this? Because actually as human eyes, we are having a limited shades of gray to be perceived at the same time. For example, if I look at the screen, I cannot have, if one spot of the screen is having a very bright light in front of my eye, okay, I will not be able to see the rest of the screen because one spot is very bright. So our eyes is limited in its dynamic range, right? And they say that the dynamic range is 30 shades of gray that our eyes can see at each particular time. Okay, but in summation, some people say that our eyes can go in what we call the from the too bright to the too dark, but we can take this gradually, right? We can reach up to, for example, 700 shades of gray. So if we take these shades of gray, gradually we can see almost 700 shades of gray. But if we look at them at the same time, our eyes cannot see except for 30 shades of gray. I want everybody to know this. So assume that this is the ratio of shades of gray that are received by the transducer, this column here, and it has two bright area here and two dark area here, and in the middle we have the mid-level echoes, which are in this area. So what happened in compression? Compression is actually more compression happen to the too bright and more compression happen to the too black. Why? Because they don't carry any clinical significance. For example, the too bright are, for example, reflections of bone. Okay, reflections of bone are, if they carry any information about the bone is all of them are bone. So I don't have any significance if I'm having very bright or very, very bright or bright. So they are all bright. Okay, so this doesn't carry any significance for us. Or stones, for example, right? Also in the dark, they are anechoic fluid. Okay, it's very deep anechoic or a little bit anechoic. So what happens here? They are all fluids, right? All natures of fluids are gathered, all of them in one description, which is anechoic. So these two ends, the too bright and the too dark, are compressed much, and that's why they are here in these areas. So the strongest signals, the bright display, they remain bright. Yeah, in compression, they're still bright, but not that bright like here. They are compressed, all of them compressed to this level, for example, and this will be given here in the image. Same story happened to the too dark. I'm giving here the too dark or the too black. Okay, they are all compressed at this level of black, and they are given here. So these ends here, the too bright and the too black, are still black and white. Okay, so the strongest signals, the brighter, still bright. The weakest signals, the dark, still dark. Okay, so what happened here in the middle, in these are the mid-level echoes, okay? They are still compressed, but not much. The compression is not much in this area, the C, the area of the mid-level echoes. Why? Because these are representing actually the tissues we are scanning. The tissues we are scanning, they have mostly mid-level echoes. They are variable mid-level echoes, but still they are in this location, in the area of the mid-level echoes. So the number of shades of gray are adjusted by compression between what? Between this area and this area. The rest here are adjusted by compression. So let's have um, more or less applicable examples of the compression on the effect on the screen. Okay, this is here a picture, the same liver, okay, and there is a point here to an area that it looks like a little different, but we don't know what is this area. With this picture is more compressed. There is a lot of compression here in this area. What's happened here? The dynamic range is lower, meaning that I'm having less shades of gray, lower shades of gray. So the picture here, the shades of gray are limited. I cannot get all the shades of gray that I need to display each specific point in the screen. That's why you see here, some of the points are a little bit more brighter and some of the others are more darker, but the ratio of the shades of gray is limited. Because what? Because I'm having here more compression. This picture is more compressed. What happened here? This area, this picture, we call it, it's a high contrast picture. The word contrast here is we are adopting a word from the photography. This picture is a contrast picture, meaning that a high contrast picture, meaning that the dark are more darker, the brighter are more brighter, and the number of shades of gray in the middle, they are less, okay? So this picture, we call it a high contrast picture. But what happened here if I apply this to the ultrasound field, okay? I'm looking for resolution, I'm looking for diagnosis. All right, is this picture here helping me to diagnose this area, which is the pointer here? Okay, we don't know much about this area. So why? Because the shades of gray for this point and the next point are almost close to each other. That's why, because we don't have enough shades of gray to represent these 2 points, okay, I'm losing the distinction between this and this. I'm losing the resolution. That's why we call this picture a lower contrast resolution from the point of ultrasonography. So from the point of uh, uh, photography is a high contrast picture, but for the point of ultrasonography, it is a lower contrast resolution, right? I cannot see much about this area. I need more shades of gray to see. Now we go to the next one here. This next one here is we apply less compression. When you apply less compression, what happens? The image gets a little like smoother, right? because I'm having more shades of gray that are available now to, to document or to give each point its exact shade of gray. So what happens now? This area starts to show up. Okay, if you look at here, this is like the echo pattern of this area and the nearby area. Both are mid-level echoes, right? Both are mid-level echoes, but they are not exactly the same. There is some difference, very little, subtle difference between this spot and the nearby tissues. Okay, I need some more shades of gray to let it appear. Okay, so in this area here, I can't see it clear, but when I added more shades of gray, now it started to get its own shade of gray, and the liver has another shade of gray. So I can now differentiate these two areas from each other. And the image gets more smoother because I'm having more shades of gray now that can display different echoes in the liver, right? So this one here is less compression, more dynamic range, more shades of gray. From the point of photography, this is a lower contrast picture because the two extremes, the two black and the two white, are not very apparent in this picture, so it's less contrast of the picture, right? But from the point of ultrasound photography, ultrasound, it is called higher contrast resolution. So photography is lower contrast, ultrasound, higher contrast resolution. This is by less compression. Okay, we need to know something here. For the word compression and the dynamic range, they are the opposite. So if I'm having high compression, like this, I'm having lower dynamic range. If I'm having less compression, I will have high dynamic range. So they are the opposite. Always, they are the opposite. Okay, why mention this? Because in some ultrasound machines, the manufacturer is putting the word dynamic range as if it is compression. So if you increase the dynamic range, you get the picture going to this way, right? Going to this way means that you're putting more compression, although the key is called dynamic range. So don't get confused about this. Don't get confused about some machines. They are labeled the opposite, but they mean in the same area, which is the contrast resolution of the picture. Okay, so this happens in some brands I've seen that they are putting the word compression as if it is dynamic range. Actually, compression is inversely related to the dynamic range. All right. Now we go to the fourth function of the receiver, which is demodulation. Demodulation is, from the word you can see, is changing the mode. What is the mode here? Is it radio frequency mode or is it video mode? So this is what you call demodulation. So demodulation is a function is done by the receiver. So as you see here, the receiver has 5 functions. This is the fourth function. Is it adjustable? No. It's the only unadjustable function of the receiver. All the functions of the receiver are adjustable except demodulation. What is the function of the demodulation? Is to convert the received electric signals. I'm having here electric signals coming out from the transducer to the beamformer to the receiver. So these electric signals are actually coming in what you call the radio frequency mode. Radio frequency mode. This radio frequency mode, okay? But what happens here? The display and the scan converter, they like to have what you call the video mode. So the video mode is the one that is processed by the signal processor, by the image processor, which is the scan converter. Okay, and the display they like to have in the display used to display video mode. The display does not display radio frequency mode. So this is the reason why this function is unadjustable, because if you change it, you will get the image lost, completely lost. That's why this function is kept unadjustable, right? So what happens here? Conversion of radio frequency mode to the video mode, okay? How this process of demodulation is executed or is it done? There are two steps. First step is called rectification. This is the radio frequency mode. We're having higher values, lower values, and this is the baseline. So the negative values are here, the positive values are here, okay? But for the demodulation, for the sake of modulation, all the negative values are pushed up, so they will be positive. So all the negative values, they will turn into positive values, and this will be the result here. So this is the result after the rectification. Okay, what is the next step? We call it enveloping or smoothing. What happened? Okay, I'm having now all the positive frequency or all the positive values here. Okay, they are all having like spikes or peaks. So sharp peaks, sharp edges here, sharp points. These sharp points cannot be processed and cannot be displayed by the monitor. That's why we need to put them smoother. We need to envelope. So enveloping is doing what? Is putting an envelope over these sharp peaks to make them blunted a little bit. So it's evening out. So enveloping or the smoothing is evening out of these peaks, okay? And that's why sometimes called smoothing. The sharp peaks are becoming now smoothed out. So this is the smoothing or enveloping, the second job of the modulation. So the modulation, we have two jobs or two steps, rectification and enveloping. Both are to change the radio frequency mode, which is this one now, becoming these like blocks like this one. So this is the video mode. This is the video mode, and this is the radio frequency mode. Okay, what is demodulation? Conversion of the radio frequency mode to the video mode. Last step is rejection. Again, this is adjustable. Yes, rejection is adjustable. What are the key controls? Okay, it's called threshold or suppression or reject. These are synonyms. You can find them on the screen, on the ultrasound, either soft key or hard key on the machine. What is the function of the rejection? Is to reject the low-level echoes. Okay, what does it mean, low-level echoes? The echoes that are very close to be anechoic. They are usually representing artifacts. Okay, so if you're having an area that is having some low-level echoes, right, and they are making the picture a little bit blurry, okay, rejection here will make it more clearer for you. So these are the low-level echoes. They are everywhere in the image, but they are more seen in the, if you have, for example, in a cyst or in a gallbladder or in the urine bladder, when you have the background is too dark, you can see these echoes very clear. Okay, so these are the low-level echoes. Okay, they are representing what? They are representing noise artifact. You remember noise artifact? Noise artifact is coming from what? From the contamination of the electromagnetic fields around the machine. These electromagnetic fields around the machine, they are contaminating the circuits, the cable, and they are representing as these low-level echoes on the screen, right? So how to remove them? By putting rejection. The units are, of course, decibels. Like all the units inside the receiver are called decibels. Be careful about using rejection. Why? Because all the low-level echoes that we are removing, they are not all of them coming from the noise. Sometimes we have some tissues that their representation or their echo pattern is low-level. Low-level echoes, sometimes they will be represented on the screen as clinical significant reflections. They are not noise. So be careful about the low-level echoes or the rejecting the low-level echoes, because you might remove or delete some clinical significance from some tissues. For example, if you have a very dark tumor, okay, if you put more rejection, you will convert this tumor into a cyst, right? It will be anechoic. So be careful about this. Don't put rejection too much, especially if you go over rejection now. So this is the second step. If you do over rejection, what happens? You will remove the mid-level echoes. Okay, the mid-level echoes, the mid-echogenic. Okay, you will remove them. Beside, you are removing the low level. You will remove also the mid-level. What happened now? These two reflections or two echogenesis, the low level and the mid-level, will be converted anechoic. So I will not be able to see the tissues. I will not be able to see anything. The whole picture will be mainly made of the hyperechoic structures. That's it. Others will be converted as black. So this is, again, be careful with the rejection in this situation. Rejection is a good step or a good helpful tool, but be careful about it. You might convert tissues into anechoic, which will be of bad significance to the screen, to the diagnosis. All right. Thank you. And last word before we leave this the receiver. Receiver is called the signal processor. Okay. And the next one to discuss is the scan converter, which is called image processor. I want to mention this before we go to the scan converter. The receiver is called the signal processor. Why? Because it's processing the signals that are coming in scan lines. So they are still in the form of scan lines, that series of signals, but they are still in the form of scan lines. Okay, so this is what we call signal processor. When you come to the scan converter, these scan lines are converted to an image. Thus, we call it image processor. All right. So signal processor at the receiver, image processor at the scan converter that we're going to discuss in a moment. Thank you and have a good one.